Okay, so we're going to continue from previous week to how to enlarge this. No. Right. Okay. Have you memorized the Greek letter? Not only memorize how to say it, to write it down as well. At your age now, the more you can get to expose yourself to new language that has new writing system altogether, the better it's going to be for your brain. Did you know that? Remember your botany? Was it easy to learn all the scientific Latin names? And why is that? Why? To start with, you didn't take a class with me. I think most lecturers not going to bother to teach the etymology of it. Remember? I teach you the etymology, the meaning, the origin of the word. What does it mean? Yeah. So in the future, when you get to educate other people, it's always a good idea when it comes to teaching, relate to something that your students or your audience already familiar with. Yeah. So that can enhance learning and memorization. Right. Where do we start? See it, right? Right. Okay. Right. So let's continue. We are still on the topic of water potential. So previously you have been introduced to the concept of water potential. It simply means the potential or the free energy of the water to do job or work. To do what work? Exactly. To move from higher concentration to lower concentration until the system that it is in contact with is in equilibrium. And if you remember from your, I'm not sure whether it's chemistry or your physics, did you learn thermodynamic? Yeah, chemistry. So in thermodynamic, the second law of thermodynamic is actually dealing with this. When two systems, you just leave it separately in isolation, both actually will undergo entropy, meaning that the disorder arrangement of the molecules. But if they are close to one another, they will somehow reach equilibrium and everybody stay happy. Right? Okay? Do you know entropy? Still remember? When you start off as something, it's not going to stay that way forever. If you start off with ice cube and you put it in room temperature, is the ice cube going to stay that way forever? What's going to happen to it? Yeah, it will melt because there's a disorder arrangement of the water molecule now. In the ice cube form, it's in the form of lattice, orderly molecule arrangement. As time progresses, the entropy increasing, so it becomes disorderly. Now from ice, you get your liquid. If you leave it even further, that puddle of water on the surface, what's going to happen to it? Evaporate. So evaporate the water molecules in the water vapor compared to water molecule in water liquid, which is more disorder, the vapor or the liquid? Vapor. Hence the Brownian movement. It's more rapid, random movement. Okay, so this is what we are dealing with. Water potential. So it's all in the efforts to wrong mouse. It's all in the effort to achieve equilibrium. Okay, but talking about potential energy, because we talked about in the earlier slide about the free energy. So energy, unfortunately, you are still in your thermodynamic lesson. That would be the first law of thermodynamic. Energy cannot be created nor destroyed, but can change forms. Okay, right? So just because you are learning agriculture doesn't mean that those chemistry, physics lessons are going to go away, right? You deal with this on in your life on daily basis. So got a type of energy, kinetic energy and potential energy. Kinetic energy usually you involve motion, right? Like when you want to make something to do work, you provide that particular thing with energy so that it can do its job. Cycling the bike, the energy was actually once before in the form of chemical energy. Okay, why chemical energy? Because it's in you, your ATP, your muscle, and everything. Then you start pedaling the cycle or cycling. So what's going to happen to the bike now? It's going to move. So what was once in your muscle, in your legs, chemical energy, has now been converted into other form of energy, which is the motion energy, kinetic energy. Okay, and the same thing goes to the radiant energy, thermal energy, and so on. Okay, the radiant energy from the sun that comes from our sun, the solar, comes to the earth, and then it gets intercepted by the leaves. The leaves use that to energize the process of photosynthesis. So this radiance energy, which originated like so many million kilometers away, has now become the new form of energy, which is the chemical energy in your glucose molecule, right? And then this glucose molecule can actually be later, of course, transferred to other form of energy. So you can see that all of this energy, they are just playing around in a loop, right? Changing from one form to another. Is there any process new energy is created? No, they just like passing buttons. Okay. What we're interested with water potential is surely the potential energy. Potential means that the potential of the water molecules to move. It's not moving because somebody giving it energy. No, it's moving because there are so many of the water molecules. It's at the same kind, right? And then in front of it, it's being presented with an area of lesser concentration of its own molecules. So following this law, this second law of thermodynamics, these groups of water molecules have the inclination or cannot stop itself from moving to the area in front of it, which has lower concentration, right? So that's the concept for the potential energy. Okay, even for the gravitational energy. Do you know how gravity works? Thrust bumi. What about it?
Everything attracted to it.
A bit. Is it so? If everything attracted to it, why everything attracted to it? Just a quick. I don't want to go too much into physics. If you think everything gets attracted to Earth, then that's not quite correct, because then you are treating Earth like one big giant magnet, which is in a way it is. But what if you are having on the Earth's surface something that is not magnetic materials? It is still attracted to the Earth core anyway, right? You got woods, you got stones, you got plastic, you got water, air. In our universe, there is a concept of space fabric. You know, permeating through all of us. You can't see it, but it's there. Space fabric. You see fabric? When you're talking about fabric, let's say that this is the space fabric. This is your Earth. Okay, Earth. Is it light or heavy? Heavy. So it's going to touch the space fabric, and then it will start to bend the space fabric. The heavier it is, the deeper the bend is going to be. So if you are close to the Earth, are you going to stay static or are you going to jump into it? Right. So if Earth not touching it, you have yourself here, that is the Earth, nothing going to happen because Earth is not pressing against the space fabric. But since the Earth is so heavy, then you are having the tendency to go towards the Earth. You are basically, plunging into the Earth perpetually because the Earth is sphere. So that's the concept of gravity. Okay, nothing is pulling anything. It's just you are. We call it perpetual falling. Okay, so for water potential, we are dealing with which one exactly?
Electric potential.
Electric? Is it electric?
No.
No. So the purpose is to show you water potential is just one potential. There are many under the same kind. Okay. Right. Okay. Please get this right. Okay. So water potential, you have your, why my marker like this? That doesn't look pretty. Right. So water potential, or sometimes you got the word W here, means that the total potential of water equals to, there are many components contributing to it. You have the solute potential, you have the pressure potential, and also you have the gravitational potential. Solute means whatever that can dissolve in water. Sometimes it doesn't have to dissolve. It just be present in there, and it's disturbing the water potential. By disturbing, I mean making the water potential more negative. Then you have the pressure potential, because water, can it be compressed or not? No. If water cannot be compressed, how are you using your syringe? Compress. You can compress water. And then gravitational potential. Okay, this is due to the fact that some water is not going to be on the flat surface all the time. Sometimes it's up and then it has to go down. So that actually creates potential from the higher place to the lower place. Okay, and all of these units is measured in Pascal. And since the value is usually very large, we put a prefix to it, which is mega. Mega Pascal. Mega means 10 to the power of 6. Okay. Mind you that Pascal is actually a short form of saying Newton over square meter. It's the same thing. Okay, so if you are dealing with maybe books from other countries, remember I tell you, you need to be open-minded about this. Don't get spooked. You know spooked? Jangan terperanjat, jangan cepat melatah kalau nampak benda-benda yang unusual. You need to relax. It could be the convention of that region. It's not Pascal, but they're using the Newton over square meter. So I keep on pressing on that, right? So to help you with that, I put a little unit conversion table here. So for example, you can see that when it comes to pressure, there are a number of units that can you use. Pascal, bar, psi, atmospheric pressure, and this is atomic. Anyway, this PSI, I want to highlight here, that is not psi, this thing. Okay, that PSI is not this. This is all small letter, means pounds per square inch. Okay. Can you see here? I know it's very small. That's LB. That is the symbol for pounds. 1 pound is about 450 grams, I think. I'm not very familiar with that unit, okay, because that's a very old time. And then you divide that with square inch, right? So PSI also equals to I can't need to remove this. PSI equals to pound, not pound sterling, okay? This is pound the weight, square inch, okay? Or simply inch square. All right, okay. So what's the, if you are not remembering this correctly, so take some time later to go through this, okay? Because this should be the pre-requirement to learn this. Okay, now let's look at how to calculate the components of water potential. In agriculture, in plants water use, one component of water potential is very important. That is this solute potential. Okay, and luckily there is a simple formula to calculate solute potential. Solute potential, which is minus ICRT. So what is I? It's okay. Ionization constant. C is the concentration in molar, and then R, so pressure constant. This depends actually. We use the units of liter bars over mole Kelvin. Okay, and then T, temperature, which is in Kelvin. In Kelvin. How do you get it? Degree Celsius plus 273. Okay, so let's look at this example here. We want to calculate the solute potential for this sodium chloride here. Okay, so we know that this is the formula for solute potential. The negative times ionization constant times R, which is pressure constant, times temperature in Kelvin. So the I here, ionization constant here, even though it says here sucrose does not ionize in water, therefore the value is 1. Sodium chloride, it is an ion or it is a molecule? Yeah. So sodium chloride can dissolve in water. When it dissolves, it can dissociate. Sodium chloride. How many now? 2. So that's why I put 2. Okay. Right. Sucrose, on the other hand, sucrose is that actually not really a simple sugar. What kind of sugar is sucrose? Monosaccharide, disaccharide, disaccharide. So do you think it's easy to dissolve in water? So it's gonna take some, yeah, yeah. It can if got some enzyme or something, but pretty much say that it's not going to ionize. When people say it's not going to ionize, meaning that it's not going to dissociate into its component, like sodium chloride. Okay, right. So and then 2 you times with the molarity of it, 0.25. In case you have forgotten, molarity equals mole per liter. Okay, that's why it is written this way, moles over liter. Then you times with the pressure constant. This is just a constant, meaning that some scientists have tried before to provide this value. So we just following it. So the value is 0.083 liters bar over mole Kelvin. Then you times with the temperature, which is in Kelvin. Since the temperature is 21 degree, you add 21 with 273 to get it in degree of Kelvin, which is 294. Then you will get 12.2 bars. Didn't I just say it should be in megapascal? So can you convert now? 12.2 bars equals to what? Megapascal. Remember you got that slide before? Try to calculate. That should be super easy. Convert bars to megapascal. Why is it bars? Why is it not straight to megapascal? Because of this. Ionization pressure constant is in liters bars. If it's straight to Pascal, then we can use without to change. So what does it become now?
Negative 1.22.
Negative 1.22. How do we come about that? So my 12.2 bars, my times 100,000. You get what? One, two, three, 4, 5. 1, 2, 3. 1, 2, 3. Is that correct?
1, 2, 2.
1, 2, 2. Is that correct? Okay. However, this is Pascal. The question now, it was megapascal. So you put mega, which is 6. 1, 2, 3, 4, 5, 6. Now it becomes 1.22 megapascal. Okay? Very simple. Right. Okay. Now we talk about the other components of the water potential, which is the pressure potential. Okay, pressure potential, you can see that if the water simply on the flat ground, flat surface, nothing much going to happen to it. It just stays that way. You don't touch me, I don't move. Simple as that. However, when you are in a hypothetical situation or experimental situation, like in the YouTube here, not YouTube your video, what is that thing? What's that? Fork? What's that? What is that gray thing? Pushing down and up. Pulling up. What's that called? Piston pump. There are many kind of pump. Okay, so we use it a piston pump here. Okay, right. So on this example here, you can see that when the water is pure, the water potential is always zero, meaning that there is no impurities, there is no force or pressure being exerted on it, and it is on the flat surface. It's not on the higher up location. Okay, almost impossible to achieve it. Almost, I say almost. Okay, in a very special situation, you can get this zero water potential, right? When you add the solution, what happens now? It becomes negative 1.0 megapascal. But when you add pressure, the value becomes positive now. This is the reason why the water is not going from this of higher water concentration to the lower water concentration, because the pressure is negating or neutralizing the net movement of water, right? And the same thing actually also happens in plants, okay? And this is why the plant is what we call is in isotonic situation or condition, meaning that the pressure that coming out from outwards towards the inward equals pressure that is being exerted back by the plant from inward goes to the outward. So let's see this in a more clear manner. So we've got three figures here. So the first one is in this U-tube example, the middle of it is separated by a semi-permeable membrane. On the right, you got your pure water, hence the potential of it is 0 megapascal. But on the right side of it, the scientist has added it with a 0.1 molar of solution. And this thing dissolved in the water. So when this happened, immediately the solute potential, this thing, solute potential, that's how to calculate it, becomes negative now, and the reading is negative 0.4. When this happened, there is a difference now between the left hand side and right hand side. So according to the water potential law, it will move from where to where?
From lower to higher.
Yeah, meaning that from more positive water potential to more negative water potential. This is more negative or more positive?
Positive.
Positive, right? And this is the negative. So the water will move to the right side of it. And when this happens, you can see that the water level start to rises. Okay? Sometimes it doesn't happen immediately. It takes time because you got this membrane here. Okay? Now, when this happens, the new calculation takes place now. The solute potential, you got solute potential and also you got the pressure potential now. Why there is a sudden pressure here? Do you see any piston? Okay. This is to show you that the water can exert pressure on its own weight. You don't have to provide any external force to stop the water from going upward. The water itself coming together, the weight of it, preventing the level to rise further. Okay, exerting to who? This location here. So what's the evidence of this? In other situations, can you think of any? Water weight actually causing high pressure. Can you think of any other simple example? Where? Kat mana? Tangki air. What happened in water tank? Memang semua ada pressure. You know Titanic ship? Where is it now?
Under the sea.
Where? Underwater? Underwater je?
Under the sea.
Is it floating? Is it moving, or is it completely at the bottom?
At the bottom.
Okay. That ship, is it intact? The shape of it?
No.
What happens to it? It actually exploded. It actually exploded. Think of it. When you are, I'll just draw. This is water level. This is you. This is you. Is there any water above you now? No. So you feel like 0 gram. 0 gram. Now you get into the water for 10 meter. 10 meter. Okay. Is there any water above you now? Yeah. Okay. So this water, do you think it has weight or not? It has weight. Remember, and always remember, water, pure water, 1 gram equals to 1 mil. And this is, if you are in the sea, this is salt water. That's even heavier. And let's say that the conversion rate of it 10 times. So since you are 10 meters, let's say that the water here is 100 kilogram. Then you go even deeper because you want to chase a whale. You are at 1 kilometer. So what happened to you now? Why do you die? Why do you explode? Potentially, what is the weight of the water here now?
10,000. 1 time for area.
This is 10 meter. This is 1 kilometer. So
100,000.
10,000 times 10 equals 100 kilogram plus 100 kilogram some more. 100 kilogram. So about 100 ton. Hold on, fasten your seatbelt. Yeah, we are taking a very deep dive today. 100 tons. What's gonna happen to your little body now?
Crashing. Destroy.
Unrecognizable. Right. 100 ton. No kidding. So when this happens, can you imagine if this little membrane here is you at the bottom? Will it experience pressure or not? Yes. That's why you have the pressure reading here. Okay. So that has the pressure of 0.15 megapascal, and the solute that has dissolved now also 0.15 megapascal. So the net value of it 0, which is equals to the other side 0, right? If suddenly you want to introduce further pressure by using the piston pump, you can see that because you want this level to be the same. Okay, so you keep on adding positive pressure by using the piston pump until the reading of the psi pressure is equals to the negative of psi solute. So when this happens, you will see that the level of the water, pure water on the left side is equal to the level of water on the right side. And that's when you achieve your equilibrium. Okay? If suddenly you remove the piston pump, what's gonna happen to the pressure, to the water level? It's going to go up back. Right. Okay. So having looked at this, now you can appreciate the plumbing system in the building that you are in now. Is there water in it? Yeah. Is there a pressure on it? Little pressure? High pressure? High pressure. What happens if the plumbing structure is not sufficient to withhold all the pressure? What's going to happen? No water. No, it's not the water. You'll be in the ocean first. Oh, boom. Right. 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 So when you want to have your own hydroponic system or fertigation system, you are going to deal with many little piping work. Okay. So this is the thing that you need to pay attention to. You don't want creating too much pressure until you are blowing all your fertigation arrangement, or is it going to be under pressure where your polybags at the end not receiving enough water? That's not going to do any good for your little horticultural setup. Okay, so remember that, so that act accordingly. Okay, what about the pressure experienced by plant cell? We're learning plant, right? Solid. When the osmotic pressure, due to the presence of water, pressing going into the cell, what's going to happen to the cell in here? Hypertonic. So the state of the cell is called turgid. Okay. If the amount of pressure coming in, going against it is the same, the cell is said to be isotonic, and the state of the cell is said to be flaccid. Or in your layman's term, people will say, oh, it looks fresh, it looks crisp. The vegetable looks fresh. That fresh vegetable is actually flaccid. Okay, but if suddenly in this region out here there's so much salt solution, what's going to happen to the water in the cell? It's going to go out or go in? Go out. So what's going to happen to the cell now?
It's hypotonic.
Yeah, hypotonic solution. Then you will get a plasmolysis in the cell. However, you can deplasmolyze by introducing higher concentration of water in the cell, and this only applicable to plant cells. Notice how the cell wall does not change in any situation. What was changing here? Cell membrane, yeah. Only the plasma membrane is changing. Okay? And this plasma membrane, due to the rigidity of the cell wall, it's not going to burst like animal cell. Okay? When you introduce back water to the system, it's going to deplasmolyze, and your once wilting vegetable going to be looking crispy or fresh again. Right? Okay? Right. Moving on. What's that? If you take advanced physio, which unfortunately I'm teaching as well, you're going to learn something we call as the bulk flow in plant. You see, plants do not have heart. So how on earth it manages to circulate water and solute throughout the body in the system? Right? Does plant has a pump to pump everything going on? Yeah. So one of the mechanism plants utilizes to move this entire stream of water and solute throughout its body, it's called a bulk flow. Bulk. There are a number of other methods, but this one is called bulk flow. Okay. So we start from the left. This is the xylem vessel. By the way, xylem, unlike phloem, is dead. Xylem is dead. You should have learned this in your botany. Remember your anatomy? You look at the xylem. What's the color? Ke tak tengok mikroskop? Tak ingat. So, at the bottom of the xylem vessel, you can see that the water potential, the net water potential here is minus 0.6 megapascal. As you go up and further the xylem vessel, you're going to see that the megapascal of the water potential, the total water potential here, it becomes more negative or more positive? More negative. So now, water will move up or down? Up, because that's the law of the water potential. From the positive region to the less positive region, right? So that's how you get the water to go up and then get transferred to the phloem next to it, because this region, can you see the little red dots? These little red dots usually are complex sugar. When they are present in high amount, what does it do to the solute potential? Is it going to increase or decrease it? Decrease. Any foreign material, substance present, dissolved in water, going to decrease the water potential. So that's why the purer solution move to the more concentrated solution, and then it going to go down, and eventually it's going to bring along with it, remember, okay, water in the phloem conduit now, it's not only pure water, it's actually water plus other stuff, sugars, RNA. You should know that RNA can move in the plant as well. It's not only in cell. RNA, do you know RNA? Yeah, RNA can travel in plants in the form of microRNA, small RNA. And these can move along the bulk flow and then end up at the sink cell. Sink cell can be younger leaf, can be flower, can be fruit, and so on. Right? Okay. So when this happen, much of it has been the sugar has been deposited in the sink cell. This will cause the region here to become free of solute, more of water. Okay, so when this happens, this region of higher water potential will transfer itself to the bottom of the xylem, and the cycle continues. Okay. That's how you got this stream of water and flush throughout the plant. One way. Okay. If you want to know further, take advanced physio. But fair warning, it's going to be very sad. Okay. Right. So that's all about the water potential. Before I move to the final part of the water story, any question about water potential? All good? Okay. Humidity. So what is it? Do you see the word there? It says relative. In science, the way to make your life easier so that you do not forget, relative means it is comparing with a benchmark, comparing with a standard. It's always that way in any parameters. And in this case, it's relative humidity. So it's comparing with what? That's what you're going to see. So relative humidity shows how much amount of water that is present at the moment in this air. Okay. In any area or in any volume of area, the ability of the room to hold water changes depending on the temperature, depending on the location of the room. Aku cakap apa lupa dah. Meaning that this room, let's say that the volume, the capacity of this room, let's say that 100 liters. This same room, if you bring this room to Cameron Island, which is it colder? Colder. Is it higher or lower than sea level?
Higher.
Higher.
Yeah.
So the same room, this room in Cameron Highland, the capacity to hold water is not the same as this room, which is warmer and at sea level, meaning that the pressure almost at 1 atmospheric pressure. Okay. So with that understanding, if the capacity of this warm room is 100 liter, and then you use a little device such as hygrometer to measure the actual capacity of water in here, it reads 70 liters. Remember, the capacity of this room, 100 liter. You measure, it's only 70 liter, meaning that 70 out of 100 equals to 70%. And this 70% is the relative humidity. Right? It is comparing itself to the maximum possible capacity to hold water for that particular place, for that particular temperature. It is as simple as that. Right? The same room, you go to Cameron Highland, 100 liter capacity, 100 liter size like this. However, the capacity to hold water is not going to be 100 liter. Why? It's going to be less, actually. Maybe about 80. Why is that? Why colder, higher room can hold less water compared to a warm and sea level room? It's something to do with the let me see which physics principle is that? Partial pressure. Did you learn partial pressure?
Yeah.
Okay. So when the air is cool, the air is actually contract. It gets smaller, meaning that there is less room for the water vapor or any gas to occupy the place. This room is still the same size, but the capacity to hold is less. Right? Warmer room, it's actually expanding. Remember, ever heard the air expands upon heat? So it expands. When it expands, it has more room to fill in with more gas. Yeah, right. So that's what happened here. So let's look at the example here. So BACD, air temperature for B25, maximum absorption is 23 gram per cubic meter. Let's say that this, let's just say this is 23 liter. And you only measure 11.5. It makes the RH for this B room is 50%. The same room, if you measure the water as 23, and 23 is the maximum capacity to hold the gas, the water relative humidity for it is going to be 100%. Right? So the same room, this is Sablang UPM room. Now it undergoes cooling. It goes to Cameron Highland. The same room now. Air temperature 14. From 25, go down to 14. That's like 11 degree cooler. Look at what happens to the maximum absorption now. Only 11.5 liters. It's the same size. Yeah, it got half of it because the air is now has contracted. So there is no room to fill in with gas, right? So relative humidity is going to be 100. When you measure the absolute humidity or the water level in there to be 11.5 liter, which is the maximum of it. The same room, if there is further water present, because the water may be actually you want 23 liter water to be present in the room, but this 23 liter can only half of it turn into water vapor. what's going to happen to the remaining of the water? It's going to do the condensation. Condensation is happening when the water capacity of the room has filled to RH 100%. There is no more room for water vapor, water molecule to be in the state of gas. Now it only have two choices. Either it proceed to become plasma and you got lightning in your room, or it go one step down, which becomes the liquid. And that's when you see all the water droplets on the surface. And in fact, this is the concept of the dew point. Okay, so that is the point when water can no longer stay in the air but start to appear on the surface that you can actually see. So this is called the dew point. Right? Okay, so this is, I just put it here to show you that how temperature increase the capacity to hold water. Okay, so this concept is very interesting and important, especially when you work in glass house. Okay, you're going to see in a bit. RH is only part of it. So how is it going to be useful? Because RH, it combines the underlying information about temperature, about the pressure, and also about the atmospheric pressure where you are now. If you only measure the water or only solely measure the temperature, you don't really know when the dew point is going to happen. But if you bring these two together, you can actually predict RH is already 80%. We need to be prepared because the dew is going to appear on the surface now, and that might actually hurt the electrical components. Right? Okay. Going on. This thing. This is actually for the advanced physio. Not to worry, I just want to mention this because remember in your final weeks, week 13, week 14, we're going to do the instrument demonstration. In that instrument, you are going to see this unit, VPD, which stands for vapor pressure deficit. It's actually the measure of whether the leaf is hot or otherwise with respect to the RH. I need to think how far I want to go with this. Let's put it this way. When you have a leaf, your leaf has an inner tissue, right?
Yes.
The inner of your leaf, despite of whatever happened outside, the RH in your leaf always 100%. Always. It's got water in the form of liquid in the cell. It's got water in the form of gas in between the cells. We call it intercellular water. Outside the leaf, you have RH, which is, of course, going to be not 100%. Okay, it's going to be lower. So the difference between your RH in the leaf, internal, and your surrounding air quality of the leaf, there is a difference, right? This is VPD. Right. So what is the implication? This is what we're going to see. The implication is this. When you have, I'm not sure whether I got this. Oh, don't go there. When you have low VPD, it will, in a way, tells you that the temperature of the leaf and the surrounding is rather cool or down, and the RH is high. Okay. However, when you have a high VPD value, you don't have to look at the temperature of the leaf or the surrounding. You are just being presented with the VPD value, then you can make your own conclusion. You will know that the temperature is actually higher, but at the same time the RH is low. Right. So the implication here, low VPD, you will have low transpiration, meaning that your plant is not wasting water. Low VPD facilitate the opening of stomata. Stomata opening, is it good or not? It is good if the stomata opening, but the water is not losing so much. That can be achieved with low VPD. However, if the VPD is high, the stomata kind of closing, but the transpiration is revved up, it's increasing, meaning that the leaf now is experiencing great water loss. When this happens, usually what is the look of the plant physically? Is it going to look fresh or is it going to look wilting? Yeah, wilting. Okay. So the implication is the stomata are going to closure, the plant's probably easy to wilt, and there's one more. Maybe it's not mentioned here. High temperature, high transpiration causing the plants to absorb more water to replace whatever that has lost at the leaf level. Remember, okay, water from the soil is not only H2O. When the plants absorb water, it comes with so many solute. Potassium, nitrates, and so on. And also kind of heavy minerals, right? Calcium deposit, magnesium, and so on. And this can be detrimental to the plant because the plant only needs a little, not too much. Okay, but they can't control it if the absorption from the root is happening at a high rate, right? Yeah. So just a quick repeat. When the grow room is dry, the plants will transpire because it needs to cool down. When this happens, moisture from the leaf will lose faster, exiting the stomata. When this happens, the plants will uptake more water from the soil. And water from the soil is not only pure water, it's actually a solution, the soil solution. And when this happens, more nutrients are taken, increasing risk of toxicity. And this is what you do not want. Right? And this actually has been proven with rice culture, rice cultivation. How farmers grow rice? How farmers grow rice? Do you know? Siapa tak pernah lihat pokok padi? No, pegang. Lihat mungkin you got your Google image, right? FYI, I am UPM rice scientist. Rice culture, rice cultivation. Are you horticulture? Okay. So usually you're not going to learn about rice, but I'm going to tell you. So pay attention because this is a good example why you should not allow your plants to absorb due to transpiration too much. Rice culture, rice cultivation has two methods. The wet method, which is regular rice field, flood, and then the dry method, which is called the upland rice or hill rice, padi bukit, padi huma. So wet rice culture, dry rice culture. In the wet rice culture, you're going to get your rice, the beras. The dry also you get your beras as well. And these two rice grains, when it is presented in market and when we do the sampling, guess which rice is going to have more arsenic in it?
The wet. The dry.
I just want to see how you think about it. Who says the wet rice is going to have more arsenic?
It might be wet.
3. Who's going to say the dry rice is going to have more arsenic? Hey, come on, lah. You need to participate in the lesson. Come on.
Let's just move.
I think it's wet
Then no.
because they accumulate that.
Always arson.
Where? Which one do you think?
Where?
Where? Why?
Because like the plant take more water and like the water transpire and the heavy metals stay in the plant.
Yeah. That's true. That's true. But think about this. So this so-called brown rice that originates from the dry rice field, like the barrio. Barrio is actually not wet, okay? Barrio rice. Barrio rice is actually on the hill. Padi bukit, padi huma. I'm not saying that barrio is the example here, but similar rice like barrio. When they do the study, apparently rice that has not been polished, the brown rice that you think is so healthy, is the one that has more heavy metal in it.
Oh.
Mm, yeah. Yeah, it's true. The brown part that has been polished, which is the rice bran, the bran layer. The bran layer contains so much vitamin and minerals, especially vitamin B. Remember you learned last week the alluron layer? That's the bran layer. Yeah. Yeah. Rice is hyperaccumulator. Okay. When it is presented with water, no matter how much the water, it's going to transpire a lot. Less water, it will transpire. More water, it will transpire even more. When this happens, it will start to accumulate all these not only nutritious mineral, but also the detrimental minerals, including arsenic and mercury. Right? Okay. So if you go to supermarket, if you want to buy the so-called healthy rice, you might want to think a few times. What are you actually eating? So yeah, brown rice is expensive. Why is that?
I don't know.
Okay, in terms of the milling steps, the white rice has more steps because it needs to be polished. So you need to turn on another factory just to do the polishing. The brown rice, remove the husk and then you're ready. Less step. But why brown rice is more expensive compared to white rice? Even though it has less step. That has something to do with the production cost. Why is it? Brown rice, less step to produce. No need polishing. It's more expensive. White rice, more steps to produce because of the polishing, but it is cheaper than brown rice. How come? Think. Why? The answer is actually due to this thing. I just mentioned this thing is actually what?
Because it has less alluron fatty.
Okay, then what happened? Brown rice, it has alluron layer, the brown layer, right? That's not only nutritious to human, but also nutritious for parasites or microorganism. Therefore, brown rice, the producer needs to spend extra for the storage, for the packaging, for the transport. Otherwise, the brown rice is going to spoil easily and very quickly. So extra costing to protect the rice. White rice do not have this brown layer. So less attack from all these microbes because it's less nutritious. Yeah. So the producer save on that. Alright. Okay. So this is what I keep saying to you. In science, do not think. What's the word? One way. Do not think linearly. Don't think linearly. It's so much out there that you need to see so that you can formulate this intricate thoughts process. All right. Okay. And don't worry about this. This is for the calculation actually. Maybe we'll turn this into quiz later. All right.
When is it?
Now. Jangan tanya. Okay. This chart. This is important about the relative humidity and with respect to the temperature. You see, it's color coded there. Your horticulture, right? This is very important for you. You see that when you want to grow your plants, based on the growth phases of the plant, you want to keep your plant within the happy region or accepted region by having respect to our age and also the vapor pressure deficit. You can see that if your temperature, surrounding temperature, is about 30 degree, like in UPM now, you should not have your glass house relative humidity in this region from 35% to 70% or 65%. That will make your plants is actually rather dry. The VPD is going to be low. So your plants have the higher tendency to wilt or to grow slower. Right. So the perfect value is about 65, 70, 75, 80, the greenish region. So that's the recipe. However, if you keep on adding the humidity until it reaches the grayish blue region, what will happen? That's also problematic actually. You will start to get condensation in your glass house and you will start to get a very massive fungal attack. And then you need to spend more to eradicate the fungus. Right. So you have your own culture, your cultivation to take care about, especially the indoor. It doesn't have to be glass house. It can be your little growth chamber. It can be your mini plant factory at home, anything. So this is the combination, more or less, how to guide you. Sometimes you can only change either one. You can control humidity, but you can't change the temperature. So the key here is, look what you cannot change. Then that's the one that you that's the one that you keep constant. But the other components, either humidity or temperature, is the one that you play around. What's the goal? To be in the green region, meaning that the plant is not too hot or too dry, and the plant is not too wet or too soggy, that causing the fungal attack. Right. And this is not going to be true actually from the beginning until the plant harvest. It's going to change. During the seedling, the juvenile phase of your plant, it's actually okay to be on this slightly grayish region. But as the plant approaching maturity, senescing, and ripening, it's okay to approach on this orangish region. Seedling, vegetative, reproductive. Seedling, start from here. Vegetative, the green part, and reproductive, the orange part. Okay. Don't go to the either extreme. Don't go to the completely blue or completely red. Your plant's not going to be happy, and actually when you go into your plant factory, you will be having trouble to breathe as well. Right? Okay. Yep. So that's the one little thing to show. Actually, I've mentioned this to show you that lower VPD, low transpiration, which is good, enhanced conductors, stomata openings, However, the plant may be vulnerable to disease. Why? Because the stomata open. When stomata open, stomata are holes, okay, microscopic holes. When they are open, all the fungus mycelium can get into it, aphids and stuff. But when the VPD is too high, stomata closed, the plants are protected. However, the conductance is low. Conductance means the rate of gas passage in and out of the plant. When you say stomatal conductance, you are measuring the gas exchange, the gas passage. Gas can be anything that is at the moment. It can be CO2 gas or it can be H2O gas. Okay, so that's the word conductance. And the symbol for conductance is G, universally. You're not the only one learning conductance. Electrical engineers, electronic student, learning conductance as well. You know, conductance to electricity. Pilot learning conductance as well because they need to understand how the plane works. Right. Right. And that's, oh, this is resistance. Soil resistance, step resistant, leaf resistant, and air resistant. Okay, I think that's all. Yep. Yay, habis. Yay. So, that's one. Okay, are you done with your assignment?
Yeah.
No? Ask what? Ask that. Apa? Assignment or this lesson? Maybe, is it long?
No, no.
Uh,
I just want to ask about the ground.
apa tu? Mana? Yelah. Kau nak tanya kau, ya apa benda lah. Orang nak tanya, you should be ready with the thing you want to ask. Bukan kata, sekarang ke? Dah tadi kau yang nak tanya. Any question about the water stories? Yeah.
Is the low BPD
Yeah.
causing stomata open
Yep, true.
because of the diffusion
Stomata open simply because humidity is high. It's cool. Stomata is made up of gut cells. On the gut cells, there are antenna, receptor. And this receptor, they will determine whether it's hot, whether it's cool or not. When it's hot and when it's dry, the gut cell will deflate and close the stomata. Yeah. So when that happens, meaning that the leaf is actually experiencing higher temperature. Yeah, yeah. So when stomata close, doesn't mean that the CO2 cannot get in or out. Can, but at lower rate. Water as well can go in and out as well.
So the stomata opening and closing relative to BPD is directly related to temperature.
Yeah. Yeah. So do you need open stomata all the time? Not quite. No, not quite. Yeah. 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 When stomata open, while the plant is not experiencing water stress, it's good because CO2 can in and out all the time. Yeah. Oxygen exit, CO2 in. You get more photosynthesis. Baru nak ambil. Lepas tu, janganlah buat perangai macam tu. Bukan, kau nak belajar kan? You want, if you want to learn properly, you stay young kan? You need to have this mindset of step in. What you have waited, what you have allowed to pass by, let go, will not come back. Ambil nota tadi. Who knows that while I was delivering the lesson, you doing the jotting down, that could actually last longer sampai hari kau masuk lubang. Yeah. I got all this lesson. This is something that I learned 20 years ago. It's not like I do the revision sampai sekarang pun tak ada pun. Sebab apa? Just Take a note lah. Yep. Ada soalan? Ada bangkangan? Okay, so let's see what's gonna happen on Wednesday. Nak kelas ke nak cuti? Dia kan shy cat. Nak, tak nak. Tak tahu. Sabar. What's the date for this Wednesday? Third. Okay. Kejap. No, I need to look at your syllabus dulu. Sekejap. So we have pretty much covered that lesson. Growth analysis, and we have covered the seeds, and we have covered the water. So what's left is photosynthesis, plant nutrition, assimilation, PGR. 5 left. I think it is safe if you want early holiday for Wednesday because we are slightly ahead. We are not on track. We are beyond the track now. Yeah, you are actually waving your friends at the back. Hi. Yeah. So why not come briefly on Wednesday to submit your assignment, and then if you're not clear, boleh tanyalah waktu tu. Right. Okay, and then you can take your raya holiday. Okay. And then we're going to continue back. See.
The assignment.
Hantar assignment dah 2 minggu aku bagi masa kan.
The assignment is hantar by group, right?
Yes, hantar by group, but nanti I'll come to each group to see what you have done. Okay. No, even though you submit in the group, make sure individually you do it as well. Nanti tak faham. Kan benda tu involve calculation. So, this is Raya, right? Kena datang hari Senin. Hari Senin tak cuti lagi tau.
Dia datang, dia pengenalan.
Ayalah, oi marah. Sabar. So, you come back on here and here. Kejap, ada masa tak? 10 minutes. You are going to have your mid-semester break here, correct?
Yes.
Then, this is May, 5th of May, 6th. Is this your mid-semester break? So, maksudnya this is the 7th week, right? So, 7 week. No, I'm thinking macam ni. Because on the 1st, you are not going to be having your lab anyway. Because this is Labor Day. Kan? So, you only have this one day. Maybe, macam ni. Why not on the 29th, we make it the test one day. Dah lah, 7 week. Kau nak test week 1 bila lagi? Dah 7 week, right? Dah 7 week, right? So, kenapa dia tak setuju sangat? This is 7th week already. Ha? Atau Mason, nanti Umarani marah.
Boleh.
Why are you afraid so much? Too sudden. Aku tunjuk awal, okay? Have you asked any of your senior that took my class? No. So you do not know what I'm going to do to you. Dia kan baik kau bersetuju je dengan aku. Supaya gembira. my test except final is usually open Chrome. Open Chrome.
Oh, you're not open.
Open Chrome meaning that you can go to the dean and ask, or call grandma, or whoever you want to call. Ay, sabar. Kan cakap, as a science student, don't get too spooked easily. Relax. Relax. So 29, let's turn it into, no, I tell you ahead of time sebab I potentially kena ambil cuti that week sebab I need to go, my student ada problem dekat field. So I need to be away. Even though I'm away, you have your test 1 to finish. Tapi kau tak salah bising-bising kat group lain kata, kita pun dapat awal kan? Itu namanya tak cerdik. Actually that happened one time with my group. This group, it was in 2000 kot. 2020 to 2021. Just cannot keep your mouth shut. Lepas tu duk showing off to other groups that you got things from me that your other friends tak dapat. Marahlah orang. Jangan cerdik sikit. What you get is for you. Ini bukan nasi goreng, boleh apa sharing. Kan? When you know, you know. Okay. Alright. Is that okay? Okay. Bila nak submit? Submit ikutlah. Just make sure you done. You done. Just make sure you're done. Usually kan my exam kan, my exam, even though it's open Chrome, when you Google, you're not going to find the answer. Kan? Too bad. You can ask ChatGPT, tak ada. Too bad. Okay, that is to say, maksudnya 24th, that will be our final lab class lah. Okay? Yelah lepas tu hari Isnin dah tak payah datang kelas lah. Kan nak bagi open Chrome. You want to come, datanglah. Siapa lah aku tak ada. Bye. Okay. Alright. Agree? Siapa disagree? Yeah. You need to relax. Kalau tak relax, you cannot learn the science properly. Right? Okay. Alright. So I'll see you on Wednesday, and when you come back from your Raya holiday, we'll continue with. I think we can continue with plant nutrition. Okay, learning all the elements plant needed to make them happy and healthy. Alright, that's all. So see you. Okay, welcome.